Okay, so Junior Roberts again, coming to you with real juniorroberts.com. Right, so again, we're doing a walkthrough video. We're doing a series of walkthrough videos for the January 2019 CSEC physics examination. We're on question 3, right? I've done question 1 and question 2 in previous videos. They are listed and linked below in the description of this video, so feel free to check them out if you haven't not yet done so. Alright, so we're on to question 3. So questions 3, part I, asks us to state the law of conservation of energy. Right, so this is a very foundational law of physics, and this law states that so let's start by saying the law of conservation of energy states that energy cannot be created or destroyed, but is only converted from one form to the next. Right, so that's our law of conservation of energy. Right, so energy is neither created or destroyed. It can only be transferred from one form to the next. So part 2 in the question says a goalkeeper drops a football of mass 0.43 kilograms vertically downwards from rest at a height of 1.5 meters, and we're supposed to calculate the velocity of the ball as it makes contact with the ground, and we should assume that no air resistance or wind speed is present. Now, this is a classical example where we can utilize the law of conservation of energy. But before we begin, let's make a sketch of what this is. So let's say we have our goalkeeper, right, and he has the ball, right, and he released it from this height here, and again we're told that the height is 1.5 meters. So let's say our height here, and this is the ground. So from our height here, from where we release the ball to the ground, is 1.5 meters, right? So what will happen is that at this point here, the ball will have some type of energy, right? And in this case, because it is above the ground at some height, it will have what we call potential energy, and specifically gravitational potential energy, right? And as the ball is released, that gravitational potential energy gets converted or is transformed to another form, right? And that form is, because of the ball moving, will be kinetic energy, right? So as the ball begins to move, due to its motion, it will have kinetic energy. So knowing that information, we can use that to help us to solve our problem, right? So we can say that the change in gravitational potential energy is equal to the change in kinetic energy, right? Now we know that the formula for change in gravitational potential energy is given as m times gravity times h, so mgh, right? And for kinetic energy is given as half mv squared. Now, because on both sides of the equation we have mass, so we can cancel our masses, and then we're left with gravity times height is equal to half v squared. So as we're right here now, we can look back and see that we're actually trying to find the velocity of the ball, right? So we are able to rearrange this formula to make velocity the subject. So what I'm going to do first is actually take this side over to the left and take this side over to the right. So I'm going to say v squared Well, half v squared is equal to gh. Alright, now what I can do to make v squared a subject, I can multiply both sides by 2. When I multiply this side by 2, I will get v squared, because the 2 will cancel, 2, and then I multiply this side by 2, and I get 2gh. So v squared is equal to 2gh, but we're trying to find the velocity. So we need to take the square root of both sides. So if I go over here, and I say square root of v squared is equal to the square root of 2gh. When I take the square root of v squared, I end up with v, which is what I'm interested in, and it is equal to the square root of 2gh. Right, so I can call on the services of my calculator, right, in which I'll say, give me the square root of, well, first of all, let me just fill in the values. So I will have 2 times g. We're given g as 10 meters per second squared. So that's 10 meters per second squared. Well, I need to get some more space, so let me just change colors here. So I say v squared, well, v is equal to the square root of 2 times 10 meters per second squared times h, which is 1.5 meters, times 1.5. Alright, so when I plug this into my calculator, I'll say square root of, open bracket, 2 times 10 times 1.5. Right, I get an answer of 5.48, and because it's velocity, it's going to be meters per second. Right, so that is my velocity using the conservation of energy. So a change in potential energy is equal to the change in kinetic energy. Right, so let's go further. Right, and part B asks us to define the term force. Right, so a force is merely a push, a pull, a twist, or a squeeze which changes an object's, let's say, direction, speed, or size. Right, so a force is basically a push, pull, twist, or turn, or even sometimes can be considered to be a squeeze, which changes an object's direction, speed, or size. Right, so let's move on to the remaining questions. Okay, so part 2 says that many types of forces are applied in various situations. Complete table 2 by inserting the appropriate types of forces and examples. Alright, so we have a type of force here and the example of where the force is experienced. So a satellite falling to the Earth's atmosphere is an example of gravitational, or gravity. Right, the force is gravity. Nuclear, these exist within the nucleus of atoms, right? Because nuclear forces are the forces that hold the subatomic particles of the nucleus together, right? And then when a comb is rubbed and it picks up small pieces of paper, is an example of electrostatic forces. Right? Now, magnetic we can say that exists between the poles of magnets. Right, so that's our table completed. Right, there are no more questions on this page, so we're going to go over to the next page to complete this paper. So now part C in the question says, a class of physics students conducting a school-based assessment on the relationship between force F and extension E for a rubber band, and one of the groups produced the following graph from the results. Now there are some questions for us to answer based on this graph, so let's look at these questions now. So it says now, state the mathematical relationship between force and extension in this segment, right? So if you remember Hooke's law, states that the force and extension of a spring is directly proportional, right? So we can say now that the force is directly proportional to the extension. Right, and we can see this in the graph right here, because I have extension on the x-axis and force on the y. And as the force increases, the extension also increases. So they exhibit a directly proportional relationship. So the force and extension are directly proportional. Now, part 2 says now, state the point at which the elastic limit is located. Now, for every spring or elastic, right, there exists a region known as the elastic region or the proportional region, in which the force and the extension exhibit a direct proportional relationship. Now, there's a point within that elastic region, usually the end of the elastic region, in which any force applied beyond that region will cause a deformity in that spring or elastic. Now in this case, as we can see, the region in which the force and extension are directly proportional are between O and A, and then beyond A we start to see a deformity, because we're no longer seeing the force and the extension showcasing that direct proportional relationship. So therefore we can say that the point at which the elastic limit is located is at this point here. So the elastic limit is at point A. Alright, now give a reason for the shape of the segment AB. So we can simply say that the elastic limit is exceeded, therefore the force and extension no longer exhibit a direct proportional relationship. Right, so once the elastic limit is exceeded, right, then we will no longer see that directly proportional relationship between the force and the extension. Right, so with that we have completed question 3, and we should have scored an additional 15 marks